Okay, up to this point what we have was either we have the conductor or inductor, the capacitor or inductor is charging or discharging, and when we have it charged, we have the DC circuit. Now we want to see what's happening if we have the AC in DC sources. Now we want to see what's happening if we have AC source in the circuit. So if I have, for example, assume I have uh, the voltage sources like that, and it's going to connect it, so it's going to be the RL, so it's going to be the R1R here, and then it's going to be connected to a inductor. So I have a RL circuit, but this time if the sources is going to be function of time, so this time what we have is not constant, it's going to be a function of time. Want to see what happened in this case. So if I go ahead and for this circuit, I can go ahead and write the KVL basically. So if I write the KVL, it tells me that the voltage in this circuit should become 0, or in other format. So I have, if I start to write, so it's a VR plus VL minus VT, so it's going to be 0. So write it VR plus VL minus VT should be 0. If I rewrite that equation, it's going to be basically the VL, the voltage at the capacitor, plus the voltage at the resistance is equal to the voltage at the source, which is now it's going to be time dependent. Now if I'm going to replace this equation with uh, for the capacitor, I know that for the capacitor the VI is going to be d IT over dt. For the R we have the Ohm law, which is going to be the IT times R, and then we have the VT, which is going to be the time dependent. And now if I just rewrite that, what I'm going to have, divide everything by R, I'm going to have L over R DIT over dt plus, so divide everything, so plus IT is going to be VT divided by R. So this is and the equation that we are going to have in case that we have the single resistance and single capacitor. So we are going to have also the same thing if we have the capacitor here. So if I have the VT over time, and then we have the R, and this time instead of having the inductor, having the capacitor, and we have the R, that's going to be the C. And this time if I go ahead and write the, instead of KVL, write the KCL using the node voltage method, assuming that's going to be the I1 going through this one, it's going to be I2 go through that one, and at this point whatever voltage we have is going to be VT. If I write the KCL this time, basically it says that I1 plus I2 should become 0, and if I replace them with so for the I1 I'm gonna have the C dVt over dt is the current goes through the capacitor, and the current goes through the resistance, just difference between the current that we have. So it's going to be um, the VCT, and this one is going to be the VC also. So it's going to be VC. So it's going to be VC over time minus VT over time over the R. That's going to be 0, and then if we again do the calculation times everything by R, I'm going to get the RC dV over T over dt plus the uh, VC over T, and then take this VT to the other side. It's going to be VT over time. So this is the equation I'm gonna get. In this case, if you look at this equation here, that I have it for the RL circuit, or the one that I have it for the RC circuit, is generally they write the equation like that. So we're gonna say either RL or RC that we have. We assume that we are gonna have the equation is gonna be tau, and here look at the LR, and assume the tau is gonna be L over R, or here we consider the tau is gonna be RC, and then we can write that equation as d, basically it's gonna be dxt divided by t plus xt is equal to ft. So it's the general format that they're gonna write the equation, and in this equation, this is the equation for the RC circuit. So the tau depend, if you are in the RL circuit, the tau is L over R. If you are in the RC circuit, the tau is RC, and the xt is going to be either IT or VT, depending on what we are looking at, and the FT, again you will see it's going to be different depending on which circuit have, but the FT is basically the force response, is the how we are gonna force the current or voltage into the system. So usually they write it as this general equation. So this general equation, regardless of what it's gonna be, is gonna have a general solution. So let's go there. So if the equation is gonna be, so I'll rewrite the equation. So if the equation is gonna be dxt over dt plus xt is equal to f, some function of time, anything that's going to be. If you have the equation like that, the general solution for this one, so if it's the general solution is going to be xt is equal to the xpt plus xct. So it's the general solution for that. So let's say, so this is the general solution. So basically it means that this value should satisfy the equation here. So this is a differential equation. This one, this general solution, if I substitute it there, should satisfy that. And then we have this one, which is going to be the particular solution. And this particular solution is related to the forcing system. So it's the solution that should be satisfied when we have the time dependent source, and this one is the complementary solution. So I'll write it right. Complementary solution, which is related to the uh, the initial condition, or if there is no source in the system. So basically, the first part shows that what happened if there is a source. The second part shows what happened if there is not a source. And when we add these two together, then we will come up with the general solution. I will show you how we will do that eventually. So if you look at here, the particular solution is very dependent on the ft. So if I want to go ahead and hit right here, so the particular solution, which is xpt, it depends on is the one that's going to satisfy this equation if there's a ft there. So this is if the particular solution, we put it in that one, it's going to be satisfy that equation, dxt over dt plus, so it's going to be, so let me write it, so it's going to over dt plus xpt. So it's going to satisfy the original solution if there is a source in there. And the format of that is very dependent on the ft. And usually you are given how it's going to look like, but generally, for example, I can say for example, you are going to given this, so you don't need to be worried about that. But for example, if ft is going to be something like that, r cosine omega t, so it's a time dependent source. So if you have this, then xp, it would be something like that. It's going to be r cosine omega t plus b sine omega t. And as I said, this one you don't need to, so you're given the xp, and just know that the xp is dependent on the ft. Depend on how the ft is going to be, then the xp is going to be something. The only thing is that when you have the xp, you have to go ahead and substitute it in the original equation, the differential equation, and it should satisfy that. So this is the for particular solution. For the complementary solution, which is going to be the xt, for the complementary solution is that it's going to be there when the ft is going to be zero. In otherwise, it should satisfy this equation. So it should satisfy dxc over t over dt plus xc over xct should be 0. So it should satisfy this equation here. Correct that. So the particular solution should satisfy this equation. The complementary should satisfy this equation. So In other words, we put the complementary solution, and as I said, usually you are given the complementary solution, so you know how it is. You just need to go and substitute it here, and then solve it and find all, for example, the a and b or any other coefficient or unknown coefficient you have. Then you will come here, and the complementary solution is like that, and the xc is always look like that. So the xc and is gonna look like as k e to the negative t over tau. So let me draw a line here to make sure don't when we have these two equations, we can go ahead and put everything into the general solution, and then we have the general solution for what we have. So I'm gonna just say the steps that we are gonna take to solve the AC if you have the RL or AC. So we're gonna say the steps to analyze RL or RC. Here's what we have RC and RL with AC source. So let's get what steps we will have to take to do that. Write KVL or KCL and find differential equation for the system. So for the circuit. Remember that when we write it, first we up to this point, when we write the KVL or KCL, depending if we want the I or we want the V, usually we come with the pure differential equation, but sometimes we may have some integration in the system, in the equation, in the original equation that we write. If we comes up with the integration, so we have to take a differentiate from the entire equation, so to get rid of the integration. And when we do the example, I will show you how to do that. Eventually, you have to rewrite it in a way that you have completely pure differential equation, nothing else. There should not be any integration. After we have that, as I said, we usually have the XP. So use or I said get the particular solution XPT and substitute it in differential equation. And find any coefficient or I would say any unknown that you have in that particular, and find coefficient in XP equation. So in the second step is that you go get the XPT and put it in the differential equation you find here, because this is the solution should satisfy the differential equation. And when you put it there, as similar to what we did up to this point, we can find the unknown coefficient in XP. After that, the step 3, write the general solution as, so write general solution as xt is equal to the xp, which we find it from the previous steps, um, uh, plus x c t. Write it as that. And then for the xct, and um, substitute the xt as this and put the xct. As I said, the xct is going to be as k to the e to the power of negative t over tau, and put xct in the general solution. In other words, the general solution becomes xt would be becomes the xpt, which is we find it from this the steps 2 plus um, plus the k e to the power of negative t over tau. So this is going to be our general solution. Now that we have the general solution, and at this point we know the xp, so we know the xp from the steps 2. We know the tau depend on what type of circuit we have. The only things left unknown is the k. So to find the k, we use initial condition as x t is equal to 0 is equal to xp t is equal to 0 plus k e to the power of 0 divided by tau to find the k. So by this point we have the general. When we find the k, then we have that general solution, and that's the solution we look for that.